All right, we are going to go ahead and start getting into our systems of equations. We are talking today about how to graph systems and how to write systems. So graphing and writing the systems. We're first going to focus on a couple of specific solution types that systems have. So you have, just like we had when we were solving linear equations, that if you solved it and you had either one solution because it was x equals something, or you had no solution because your x disappeared and you had two unbalanced sides, or you had infinitely many solutions because when x disappeared completely, you had equal sides. You know, 3 is equal to 3, or negative 7/3 is equal to negative 7/3. So it's the same concept with a system. With a system, when we graph it, if it has one solution, then you have intersecting lines. So you've got two separate graphed lines here. If I can find my pink highlighter. Ooh. Hold on. So you had two graphed intersecting lines here. And what was really important to understand is when you have them written in slope-intercept form, what you would notice is that they have different slopes. They're going to have different slopes. So their m values are going to be different. Maybe one of them's positive and the other one is negative, or maybe one of, they might just actually be different numbers. So that causes them to intersect at a specific point. That point could possibly be the y-intercept, so maybe they have identical y-intercepts but different slopes, or they can have completely different y-intercepts and the point that they're going to intersect at is off of the axes, so somewhere inside of one of the quadrants. Okay, then we've got what we call a no solution system. And with a no solution system, you'll notice that when you graph it, we create what? What are these called? Parallel lines. You've got parallel lines. So what's important to understand here, when it's no solution, they actually have identical slopes, but their y-intercepts are different. So they have to have the same slope, same identical slopes, but they're going to have different y-intercepts. That's how we create a parallel set of lines, because they both have different y values for what they're crossing the x or the y-axis at. They're, this one's at like around a 3, this one's around a 2, but they're going to have the exact same rise and run. So they're following the same pattern. That is, one moves up 2 spots, so does the other line. It moves up 2 spots. They're mirror imaging each other, okay? And then we've got infinitely many solutions. Infinitely many solutions is detailed out to where even though it's 2 lines that are graphed, all you see is one line. Because with infinitely many solutions, that means every single point on the graph is a solution for both sets of graphs or both sets of lines. So that means they are exactly the same equation. They have the exact same slope, same slopes, and they have the exact same y-intercepts. Same slopes, same y-intercepts. They create an identical line. Now, typically speaking, when we have them written as a system, maybe one of them might be written in slope-intercept form and the other one is not. So visually, when you're looking at the equations, you might not see that they are the same. But once you graph it, you'll be able to tell that they are identical. Okay. Now, as a quick reminder, once again, how we graph. We always start by graphing our y-intercept first. Always start with that y-intercept. That's the point that crosses the y-axis. That's what we want to do first. And here, I'll highlight the whole thing. And then the next thing is to use the slope as our directions to move to the next point. I'm going to keep reiterating that to you guys over and over and over again. Slope is a direction for you. Slope is not a point itself. It just tells you how you're going to move. So when we've got a positive slope, if we have a positive slope, and this is my green, my light green seems to have run out of ink. So if we've got a positive slope, just remember that we're going to move up and to the right. That makes both values move in positive directions. Positive over positive gives you positive. Or you would move in a double negative direction, a negative over a negative, which means you would move down and then to the left. Both of those are negative directions. So two negatives would also yield a positive slope. Then you've got your negative slope. Your negative slope has you moving in opposite ways. So if your top value of your fraction is a positive, you would move up, but that means your bottom value would have to be considered the negative, and that would make you move to the left. Or vice versa. Maybe you're moving down to show that the top is negative, and then move to the right to show that the bottom is positive. That still creates that negative direction. Okay, once you got that copied down, go ahead and flip it on over to the back. We're going to first start off with writing a couple of systems based off of some scenarios that are given to us. So when we talk about a system, again, we're talking about two equations, not a single equation, but you're creating a set of two equations with y and x variables. So that means that you're no longer just creating one variable representation, but you have two variable representations. So let's take a look there. So our first question, Mrs. Baker bought 14 boxes of red and green paper. There are a total of 72 reams of paper. So reams is those individual, like if you look over at my cart, you'll see that I've got several reams of paper on there. They're just little packaged, right? And then when we buy them in boxes, it comes with several packs of those papers inside. The red box comes with 6 reams each, and the green box comes with 4 reams each. We want to identify the variables for x and y, and then write the system to represent the situation. You have to identify what your x is going to represent and what your y is going to represent. If you don't indicate what your x and y's represent, you won't get the correct answer. So you need to make sure that you are indicating what they each are representing. And then you have to follow through with that the entire problem. Okay? So what I'm going to do first is I'm going to identify my variables. Always the first thing that you want to do is identify your variables. So we're going to let x represent, we'll let x represent the red paper, and we'll let y represent the green paper. X is going to represent our red, y is going to represent our green. Now, based off of that, what I need to do is I'm going to create two equations for my x and y paper sets. So I'm going to first look at my first statement that I've got here. She bought 14 boxes of red and green paper. Do I know how much red? Yes or no? No. Do I know how much green? No. But do I know what together they are? Yeah. We know that combined together, it's 14 boxes of it. So I'm going to write down here the statement. It says 14 boxes of red and green is going to be represented as x plus y. If I take my red and I add my green together, I know it's going to come out to 14. X plus y is going to be equal to 14. Okay, then my next statement. My next statement says that there's a total of 72 reams of paper where the red boxes have 6 reams each and the green boxes have 4 reams each. Okay, so based off of that, I know that I have 6 each of my red. I've got 4 each of the green, and that the total is going to be 72. So based off of that statement, I would write 6 times x, because 6 of each of the reds, 6 of each of the x's, plus 4 of the y's, 4y, for each of my green, and the total is going to equal 72. And that's it. There's my system. My system is just x plus y is equal to 14, 6x plus 4y is equal to 72. And then you would be able to solve to figure out what x and y equal. We'll learn how to solve those later. But one of the solving methods is graphing. The other solving methods, we call solving it algebraically, which is using either substitution or elimination. And you'll learn about both processes in next week. Okay? What I want you guys to do is I want you to try number 2 and number 3. Okay, let's take a look here. So for problem number 2, we have Greg's has motorcycles, which are 2 wheels, and ATVs, which have 4 wheels. The store has 45 vehicles that together have 130 wheels. We want to identify the variables for x and y and then write the system. So the first thing I need to do is identify what my x and my y's are going to represent. For me, I went ahead, I'm just going to say x is going to represent the motorcycles, and that y is going to represent the ATVs. Okay, now when I am writing these out, the first thing I'm going to focus on is the fact that there are a total of 45 vehicles. There's a total of 45 vehicles. That means that if I take all the motorcycles that I have and I add it with all of the ATVs that I have, I've got 45 of them. Does everybody have that so far? We're good with that part. Okay. Then for my next equation, I'm focusing on the fact that motorcycles have 2 wheels, ATVs have 4 wheels, and that all together there's 130 wheels. So that means that if I say, okay, my x represents my motorcycles, so it has to be 2x. If I put 2y, that would be me saying that my ATVs have 2 wheels. Then I'm going to add it with my 4y, because ATVs have 4 wheels each, and all together I should have 130 wheels. And there's my answer. Okay? Those are my 2 equations to create my system. All right, let's take a look at the next problem. Creative Crafts gives scrapbooking lessons for $15 per hour plus $10 supply charge. Scrapbooks Incorporated gives lessons for $20 per hour, and they have no additional charges. We want to identify the variables of x and y and then write a system to represent the situation. So what I'm going to say is that x, in this case, is going to represent the number of hours, because we're talking about hours that they're going to spend at these sessions. And then y is going to represent the total cost. How much it's going to cost me to do these different sessions at these different spots. Okay, let's focus first on Creative Crafts. So Creative Crafts is going to give their lessons at $15 per hour and a $10 surcharge. Okay, so that means my total cost y is going to come out to $15 per hour, so 15x, plus that $10 supply charge. That's a one-time fee that I'm going to pay. Y is going to be equal to 15x plus the 10. Now, when I do this for Scrapbooks Incorporated, they're giving lessons for $20 an hour and no additional charges on top of that. So their total cost, Y, is going to be 20 times X, and then that's it. They have no additional charge, so I'm not adding anything. If you put that you're adding 0, that's fine, but it's unnecessary. And there's my system. Okay? Any questions on those? All right, go ahead and look at the next page. Try problem 4 and 5 on your own. I wanted to break them up in little chunks. Okay, let's go ahead and go over these. For problem number 4, we have a homecoming dance at Liberty High School on Saturday. Many students bought tickets in advance for $5 each. So the fact that they're saying each lets you know, hey, right there, this is a coefficient to this value, advance. Other students bought tickets at the door for $7 each. So the tickets that were purchased at the door are 7 each. So that lets you know that that's going to be a coefficient to this variable in advance. In all, there were 270 students that attended the dance. So that means that there was 290 students. That means there's 290 tickets. Whether it was advance purchase or at the door purchase, there was a total of 290 tickets that were purchased. So I placed that X represents those who purchased their tickets in advance. Y is going to be those who purchased it at the door. And then my equation, if I add the advance purchase and the at the door purchase together, it's 290 tickets. And then for the cost of the tickets, it's 5 times X, 5 times the advance purchase, plus 7 times Y, which is 7 times the at the door purchase, and that's equal to a $1,790. Okay, so there's our two equations to create our system. For number 5, they already let you know what the variables are going to be. They said Alex and Ben are going to be represented as A and B respectively. So that means Alex represents A, Ben is represented by the letter B. And then the statements here. Alex is 2 more than 2 times as old as Ben. So if I write that statement here, Alex is, that means A equals, and then the statement 2 more than 2 times Ben. 2 more than is one of those order reversing problems. That means that you're actually going to flip-flop. You're going to do 2 times Ben's age first, and then you're going to add 2 to the value. Might not seem so important right now because it's addition, but had that been subtraction, if it said 2 less than, you would have to make sure you did the minus 2 at the end of it. Okay, so just keep in mind those order reversing words. And then the statement, in 8 years, the sum of their ages will be 60. So I'm going to take Alex's age and add 8 to it, because that's 8 years later. And then Ben's age, add 8 to it, because that's 8 years later. And then take the sum of those ages, and it should be equal to 60. So there's my 2 different systems. A is equal to 2B plus 2, and quantity of A plus 8 plus the quantity of B plus 8 is equal to 60. Okay? All right, so that's our writing portion. Now let's go ahead and get into the graphing portion to show solutions to some of our systems. So go ahead and flip it on over to the back. When we are graphing, remember, you can either graph it as y equals mx plus b, or you could graph your 2 intercepts if you wanted to do that as well. You get to pick the method. If it's already in slope-intercept form, then just graph it as a slope-intercept problem. So for problem, or for the very first equation, we have y is equal to 2/3 x plus 3. When I graph it, I'm going to go ahead and graph this, and I'm going to use my pink to graph this first equation. So I'm going to circle this in pink. This is my y-intercept. My y-intercept is at what value, guys? 3, right? My y-intercept is at the point 0, 3. And then my slope, for my slope, I'm going to either, because it's a positive, it means I'm going to either go up 2 and then to the right 3, or I could do the reverse. I could go down 2 and then to the left 3. Either one of those would be perfectly acceptable. But I'm going to go ahead and graph my y-intercept first at 0, 3. And then I'm going to follow my direction up 2 to the right 3, I'm going to do that a couple of times. And then I'm going to do the reverse as well. I'm going to go down 2 into the left 3. So that way I have a couple of those points plotted. And then as always, you are recommended to use a ruler to be able to connect those together. Especially because when you're graphing it, you might not graph up to one of the points. Maybe when you do it, you might only do like 2 points, but then your intercept might be further on. Okay? All right, so now let's take a look at the next one. 3y is equal to 2x plus 15. This is actually really easy to go ahead and just rewrite that into slope-intercept form because I only have the y is just has a coefficient. So if I just divide everything here by 3, then I'm really getting the equation y is equal to 2/3 x plus 5. Y is equal to 2/3 x plus 5. So that means my y-intercept is going to be at 0, 5. And then my slope is, again, it's going up 2 to the right 3 or down 2 to the left 3. Now notice we have identical slopes, don't we? But we have different y-intercepts. So what kind of solution did I tell you guys that would be? If you have identical slopes, the slopes are the same, but the y-intercepts are different. Is that one solution, no solution, or infinitely many? No solution. It would be a no solution problem. Okay, so when I graph it, I should see a set of parallel lines. So I have my point at 0, 5, and I'm going up 2 to the right 3, up 2 to the right 3, or down 2 to the left 3, down 2 to the left 3. And when I graph that together, those lines are not going to intersect at all. It's just a nice set of parallel lines that we create here. Okay? So then I need to make sure that I note that this is a no solution, and my blue's running out as well. Whew. You could tell it's getting towards the end of the school year. My pens are running out. Okay, so this is a no solution system. Okay, let's go ahead and do one more of them together. Anybody still need this one up? Okay. All right, let's do problem number 2. So problem number 2, both of these are written in slope-intercept form, so we can easily go ahead and graph based off of their y-intercept and the slope. So let's start with the very first equation. What is my y-intercept? A 1. So we graph it at 0, 1. And then my slope is up 2 to the right 1 or down 2 to the left 1. Okay, up 2 to the right 1, down 2 to the left 1. Those will create that positive 2 or positive 2 over 1. So I'm going to go ahead and graph that real quickly first. I'm going to graph it at a positive 1 for the intercept, which would be located right here. And then I'm going to go up 2 points to the right 1, up 2 points to the right 1, up 2 points to the right 1. And I can keep doing that as often as I want. And then I can go in the opposite direction, down 2 points to the left 1, down 2 points to the left 1, and just keep going as often as I want for there as well. Okay? And I'll wait to connect that in a little bit. Let's go ahead and take a look now at the second equation. For the second equation, we've got y is equal to 3x minus 6. Notice they are different slopes. Since they are different slopes, that means it is going to intersect at a specific point. So I need to graph my y-intercept first. What's my y-intercept? -6. Good. 0, -6. And then my slope is a +3. So that means I'm going to go up 3 and to the right 1. Positive over positive. Or down 3 and then to the left 1. Negative over negative. Okay, so when I graph those, 0, -6, that means I'm going to have to go down to the -6. Okay, and then I'm going to follow going up 3 to the right 1, up 3 to the right 1, and continuously do that. Okay, or I can go down 3 and to the left 1. But if I notice as I'm going down 3 to the left, I'm not getting closer to the line. I'm actually pulling away from the pink line. So when you notice that you're actually getting closer to the other line, you kind of want to continue going in that direction. So if I go up again, 1, 2, 3 to the right 1, and then up 1, 2, 3 to the right 1, and just keep going, I'm going to notice eventually I'm going to come across something. Okay? So let's go ahead and connect those lines. Let's start with the pink. And then I'll finish off with the green. Okay, and then what point I notice is that I'm graphing or connecting at this point. They intersect at this point in common, which happens to be at the point 7 and then 15. So that means the value 715 is a solution to both of these equations. If I plug 7 in and I do 2 times 7, 2 times 7 is 14 plus 1 gives me 15. Same thing here. If I do 3 times 7, 3 times 7 is 21, and if I take 6 away, I get 15. So that point is a solution to both equations. That means it's a solution to the system. Okay, I want you guys to try problem 3 and 4 on your own. And then when you are done, you can log into Delta Math, and your assignment for tonight is on Delta Math. So as soon as you finish doing your 2 examples here, get onto Delta Math and work there. It closes at 9:30 tomorrow morning. So it means whatever you've completed by 9:30 tomorrow morning is what goes in the grade book. Okay? Okay, real quickly. You should have gotten for problem number 3, your solution should have been at -2, +1, because if we look at our first equation, our y-intercept is at 0, 3, and our slope is a +1 over 1, or -1 over -1. Then for the second graph, our y-intercept is at -3, and we are either going to go down 2 to the right 1 or up 2 to the left 1. When we graph them accordingly, we would find that they intersect at the point -2, +1. And then for our last graph, if you noticed, our equations were not quite in y-intercept form, but they're very close to it. So for y minus 6, if I just add 6 to the other side, it gets y by itself. So I get the equation y is equal to 2x plus 6. And then for the second equation, I need to distribute and combine those like terms first. If I distribute, I get 2 times x and 2 times 1, so I get 2x plus 2. And then I still have this plus 4. Well, I can add the 2 and the 4 together to also get the exact same equation, y is equal to 2x plus 6. So since they are identical equations, that means that they are infinitely many solutions. They will overlap everywhere. So last question was infinitely many solutions. Go ahead and get working on that Delta Math.